Hello and welcome again. I'm Bob Falconer. This is part B of the second in the series of presentations about the MARFLEX system of masonry arch repair and strengthening. This presentation carries on from part 2A and looks at current issues that we are facing. Then we will cover some non-bridge work and also some overseas projects that have been carried out using the MARFLEX system. As I've said previously, I'm a director of Goldhope Bridge Restoration Limited, the company that installs the system, though I will be giving a personal perspective rather than a company one. The first case study illustrates the lengths that you need to go to find causes of defects. The barrel of this railway bridge in London is perfectly capable of carrying the required railway loading, yet there were significant transverse cracks in the barrel, as we can see. Pier movement monitoring is ongoing, but it's suspected that the cracks are dormant. Research on the bridge produced a World War II bombing pattern, as shown, and this showed that two large bombs had been dropped not too far from the bridge. These could well have caused pier movement and the consequent cracks. As the uncracked barrel of this bridge is of a thickness that is perfectly capable of carrying the required railway loading, we are not proposing to design a MARS installation for the bridge. We propose to insert sufficient stainless steel reinforcement to restore the shear resistance of the barrel at the cracked sections. As it is not known whether the piers are stable, we propose to install these bars as per the MARS system around the barrel as recommended by consultants AECOM. This will not significantly increase the permanent loading on the piers. If the piers are found to be unstable, then the reinforced system of foundation rescue, patented by our sister company Stress UK, can be employed. This case study at Newcastle Central Railway Station illustrates another problem that we've been looking at. This was a series of vaults under a car park that exhibited serious cracking. The section of the vaults under investigation is under the red arrow, and access to the vaults is shown by the green arrow. This photo was taken in 2005. The cracking was in the form of a 5-hinge pattern. Our problem was that the crack pattern was the opposite to the expected pattern for vertical loading. This is the expected pattern for vertical loading, but this is the pattern that we encountered. There was no sign of movement in the piers. Here you can see two tension crack that side, which is equivalent to these cracks, and compression crack at the crown. So what was the cause? The vaults had been built on a slope, and there was a suggestion that the upper vaults were pushing the lower vaults sideways. However, for this to have been the case, the damage would have been asymmetrical and the piers would have exhibited cracking. We looked into the history of the vaults. It turned out that the car park above had been part of the railway station, and it was suspected that there must have been a building above the vaults under consideration. The logical place to found such a building would have been over the piers, as shown. The foundations would have exerted pressure on the vaults, as shown by the red arrow. This photo from 1958, unearthed after our initial investigation, confirms that the car park was once a functioning part of the station. A building over the vaults under investigation can clearly be seen. This goes some way to confirming our theory. Even though the source of the problem has been removed, the vaults are in such a precarious state that they need to be stabilized as soon as possible. This is a railway viaduct where drumminess had been detected in 3 spans and ring separation was diagnosed. The proposal was to remove the bottom ring in the areas where drumminess was detected and insert new bricks. We were asked to comment. Unfortunately, the proposal shows a lack of understanding of the mechanics of masonry bridges. These are constructed on centering, When the centering is removed, the barrels sink through self-weight, which puts compressive stress into the bricks of the barrel. The addition of fill applied symmetrically further increases the compression into each ring of the barrel. If bricks are removed locally from the bottom ring, then this compression redistributes itself into the bricks around the area from where the bricks have been removed. When recasing, the replacement bricks are unstressed when they're inserted, so they never pick up the compression that is inherent in the bricks around them, and the arch barrel can never regain full strength. Recasing thus weakens an arch barrel, and this can only be considered as a cosmetic repair. If the recased bricks are not pinned to the barrel, they rely on tension in the mortar, and as this deteriorates through time, the bricks under vibration from railway loading will probably drop out. The network's rail standard detail, as shown here, should come with a health warning on the use of this detail. Note that this wouldn't work in road bridges, as the stainless steel anchors, here, here and here, would corrode in the salt water. If the drumminess was determined using an all-metal hammer, then it should be remembered that the results of such a test are subjective, and, from experience, two colleagues can come to very different conclusions on the same bridge using this test. This railway viaduct had been strengthened, in inverted commas, using radial anchors. Unfortunately, cracks were continuing, as we can see, and the anchors were corroding, with some were dropping out. Work hasn't started yet, but the proposal is to cut off the anchors and insert the MARFLEX system to bridge the cracks and install the integrity of the barrel. The MARFLEX system is ideal for railway underbridges, as the MARFLEX has some flexibility and dampens the vibrations from rail loading. We not only have to design the MARFLEX system for vehicle loading, but in this case of a culvert running under buildings, this is the culvert here, 400 meters long, we had to work out the foundation loads from buildings over and design our reinforcement accordingly. The culvert was in a very poor state, and a great deal of remedial work had to be carried out. This shows the state of the culvert. There are a number of partial collapses, including foundation failures, which endangered the stability of the buildings over. These collapses had to be reinstated. Most of the culvert was in compression only, and the MARFLEX system was only installed in the sections where it was required. This is a Grade 1 listed building and was the home of the architect Robert Adam for a time. A problem with buildings like this is they have vaults under the roadway, and these have to be maintained to highway standards by the owners. You can see here there's 5 vaults under this road and 2 vaults under that road. We've strengthened quite a few of these in London, and they each have their challenges. Some have suffered from partial collapse, which is not good news in a busy London street. Some have been undermined by tunnelling underneath. You have to be inventive when installing the system with the remedial solutions such as grouting and underpinning. And we can see here, with all the coal holes and entrances, etc., the direction of the MARFLEX system has to fit in with the contours of the barrel. This was a railway underpass in Australia. We designed the MARFLEX system, but obviously we didn't install it, even though we'd have loved to have done so. It was the idea of an engineer who moved from the UK to Australia and saw the MARFLEX system as a solution to his problem. Made a reasonable job of installing the system. This case study is a 170-meter long viaduct in northern Iran. It's of open spandrel construction with 2 40-metre square spans and a total of 9 10-metre spans. It's reputed to be the largest masonry bridge in the world, though I don't really know if that's true. The barrels of the main spans are exceptionally thick at 1.24 metres. We did this job through our colleagues at Halifax, and we designed the MAR system for the main spans. Our design was checked by international consultants using the nonlinear finite element method. A local team installed the MAR system as shown. That's the MAR system installed there. The installation and service has been monitored thoroughly, and at least one academic paper has been written about the bridge performance. We can see radar monitoring there. It's not clear whether the authors of this paper were aware that the bridge had been strengthened when they carried out the study. I should add that when we carried out the design of the strengthening system for this bridge, we believed it to be in Turkey, and indeed the materials were supplied to Turkey. It was only after the monitoring papers were published that we found out that the bridge was in Iran. This chart shows the criteria used in the selection of the MAR system for strengthening. Note that even getting the materials from the UK via Turkey, it's still won on points. It's interesting to note that they looked at the technical consideration, historical consideration, technology, durability, etc., but environmental factors weren't taken into consideration. If they had been, then the system would have won hands down. Finally, this is a bridge in India that we are currently looking at in conjunction with Halifax, India. At first, when you look at the arch supported on crates, you think it's a bit of a botch-up. However, if you compare this to the bridge infilling crimes committed in this country, you begin to appreciate its brilliance. Floodwater can still flow through the crates and fauna can still get through. When the MAR system is installed, the crates can be used on another bridge. So they're a very environmentally friendly temporary solution. As a final anecdote, our Halifax colleagues in India arranged for my wife and I to have afternoon tea, it was coffee, with the local Maharaja. My wife is embarrassed by this photo as her pashmina slipped off her shoulders when we stood up for the photo. We were taken to this magnificent palace and shown to a balcony room. He was a lovely man, and we were in the middle of conversation when we heard gunfire in the background, plus the odd explosion. He looked a little uncomfortable and then pulled his phone out of his pocket. He'd been playing war games before he came down to see us, and the game has started again in his pocket. There was much relief all round. I do hope you found these presentations interesting and that they have been able to give you a flavour of our work. The next presentation will cover the theory, testing and validation of the MAR system.